In this video, we learn how to make simple program in C code for AVR Microcontroller, to control the flashing of 3 LEDs in serial, parallel and random flashing modes. To do this, we will use 3 input-output ports of the microcontroller. We will cover the pseudo-random number generation function. Also, we will try to use the analog-digital converter built into ATmega328p, to read the voltage level on a pin that is floating, as seed values for random number generator. We will assemble the electrical circuit to check the work of program code. The executable program code as hex file will be uploaded into microcontroller flash memory using software Everdude, and Onis Programmer. How to do this is detailed described in previous videos. Open the ATmega Studio. Create a new GCC executable project. Don't forget to specify the ATmega328p in the device list. Open the file main in the main source editor area of ATmega Studio. Type the code of program. Telling controller crystal frequency 16 MHz. Header to enable data flow control over pins. Defines pins, ports. Header to enable delay function in program. Header defines 4 variable types, several macros, and various functions for performing general functions. stdlib is a utility functions such as string conversion routines, memory allocation routines, random number generator. Defines pins of the chip input-output ports for attaching LEDs. LED 1 connected to port B pin 0. LED 2 connected to port C pin 1. LED 3 connected to port D pin 2. Defines the settings for options, the modes of blinking LEDs. Number of repetitions of blinking for each modes. Settings the delay time of blinking for each modes. 200 milliseconds delay. 500 milliseconds delay. 700 milliseconds delay. 1 second delay. Definition of a function to execute a timing delay in milliseconds for the AVR microcontroller. The mode of delay is set by function in parameter, nDelay. To make a delay of 200 milliseconds. To make a delay of 500 milliseconds. To make a delay of 700 milliseconds. To make a delay of 1 second. Definition of a function to set microcontroller input-output ports configuration. Set all pins of the port B as output. The data direction register B allows us to make the bits of register B input or output. Writing a 1 makes them output, while a 0 would make them input. FF in binary notation, its all 8 digits is 1. Write data on port B, set all pins of port below which turns it off. To do the same for ports C and D. Definition of a function to blink LEDs in serial mode. The config of mode is set by function in parameters. A for loop is a repetition control structure that allows you to efficiently write a loop that needs to execute a specific number of times, that in this case depends on the function parameter, number repeat. This line gives a 1 to the pin LED 1 of port B. Therefore, the LED attached to pin LED 1 of port B will turn on and light up. In this case, a binary left shift operator is used, which a left operand's value is moved left by the number of bits specified by the right operand. To make a delay. This line gives a 0 to the pin LED 1 of port B. Therefore, the LED attached to pin LED 1 of port B will turn off and light off. In this case, a binary AND Operator is used which copies a bit to the result if it exists in both operands. The logical negation operator is also used here. To make a delay. To turn on the second LED attached to pin LED 2 of port C. Creates a delay. To turn off the second LED attached to pin LED 2 of port C. Creates a delay. To turn on the third LED attached to pin LED 3 of port D. Creates a delay. To turn off the third LED attached to pin LED 3 of port D. Creates a delay. Once more the second LED turns on and turns off. Definition of a function to blink LEDs in parallel mode. The config of mode is set by function in parameters. The for loop executes turning on 3 LEDs at once a specific number of times, that depends on function parameter. To turn on the first LED. To turn on the second LED. To turn on the third LED. Creates a delay. To turn off the first LED. To turn off the second LED. To turn off the third LED. Creates a delay. The for loop executes turning on second and third LEDs at once a specific number of times, that depends on function parameter. To turn on the second LED. To turn on the third LED. Creates a delay. To turn off the second LED. To turn off the third LED. Creates a delay. The for loop executes turning on first and second LEDs at once a specific number of times, that depends on function parameter. The for loop executes turning on first and third LEDs at once a specific number of times, that depends on function parameter. This statement is definition of a function to blink LEDs in random mode. The config of mode is set by function in parameters. The for loop executes turning on LEDs in random order a specific number of times, that depends on function parameter. This statement returns a pseudo-random number in the range of 1 to 7. The number in binary notation defines the LEDs that will be turned on. Turn on the first LED, depending on value of generated random number. Watch how it works. turn on the second LED, depending on value of generated random number. And turn on the third LED, depending on value of generated random number. Creates a delay. To turn off all the LEDs, the RAND function in C gives a pseudo-random number generator. The RAND function uses a formula that calculates new random numbers, based on a formula that includes the previously generated value. So where to get the starting point for the first number in the formula? The standard C library maintains an internal state for the random number generator, and functions RAND can seed this state. What to pass to this function? A trick you may be able to use, depending on your setup, is to use the analog-digital converter to read a voltage level on a pin that is floating or otherwise not tied well to a particular voltage. Now it's time to talk about analog-digital converter. For transferring external continuous information, analog information, into a digital computing system, we must convert them into integer, digital, values. This type of conversion is carried out by analog to digital converter. The process of converting an analog value into digital value is known as analog to digital conversion. In short, analog signals are real-world signals around us like sound and light. Digital signals are analog equivalents in digital or numeric format which are well understood by digital systems like microcontrollers. Analog to digital converter is one such hardware which measures analog signals and produces a digital equivalent of the same signal. AVR Microcontrollers has an inbuilt analog to digital converter facility to convert analog voltage into an integer. AVR convert it into 10-bit number of range 0 to 1023. Note that we have an analog reference, ARF, voltage also, which will be considered equivalent to 1023, and any voltage value less than this ARF will have less number than 1023. The input range is 0 to ARF and digital output is 0 to 1023. Here 0 volt will be equal to 0, and ARF divided 2 will be equal to 512 and so on. The ATmega328p comes with a 10-bit, 6-channel inbuilt analog to digital converter, so the controller can detect a sense a minimum change of 5 mV, so if the reference voltage is 5 volts. So for every 5 mV increment in the input we will have an increment of 1 at digital output. First of all we need to enable the analog-digital converter feature. The analog-digital converter control and status register allows us to enable the analog-digital converter and set the sampling rate. Bit 7 is analog-digital converter enable. Writing this bit to 1 enables the analog-digital converter. By writing it to 0, the analog-digital converter is turned off. Bit 0 to 2 are analog-digital converter per scalar select bits. These bits determine the division factor between the oscillator frequency and the input clock to the analog-digital converter. We will first initialize the analog-digital converter with the following code. Enable analog-digital converter, by setting ADC enable bit, of analog-digital converter control and status register A, and set the division factor between the oscillator frequency, 16 MHz, and the input clock to the analog-digital converter as 128. Select channel 0 by default using the analog-digital converter multiplexer select register. Bits 7 and 6 are reference selection bits. These bits select the voltage reference for the analog-digital converter, in this case it is AREF, internal voltage reference turned off. So, bits 6 and 7 can be left set to 0. Bits 0 to 3 are analog channel and gain selection bits. The value of these bits selects which combination of analog inputs are connected to the analog-digital converter. We are going to choose channel 0. The function performs analog-digital converter initialization in accordance with our settings. Enable analog-digital converter and set per scalar to max value, 128. Select the required channel for analog input is connected to the analog-digital converter, in this case it is channel 0. Let us write function to read the result of analog to digital convert. Wait for some time. Start the conversion by setting ADSC bit in analog-digital converter control and status register A. Wait until conversion complete. ADSC bit will be 0 after completion. Wait for some time. Read the ADC register and return the result of conversion. Disable analog-digital converter. Return the result of conversion. The main function is unique and set apart from all other functions. Every C program must have exactly one main function. Main is where the AVR starts executing your code when the power first goes on, so it's the entry point of the program. The call of the function to set microcontroller input-output ports configuration. The call of the function to perform analog-digital converter initialization. Initialization random number generator. The pseudo-random number generator is initialized using the argument passed as the result of analog to digital convert. This statement is a loop, often referred to as the main loop or event loop. This code is always true. Therefore, it executes over and over again in an infinite loop. It never ceases. The call of the function to blink LEDs in parallel mode. The call of the function to blink LEDs in serial mode. The call of the function to blink LEDs in random mode. This line is never actually reached. OK. Programming is complete. The final step is the building the project. It means compiling and finally linking all object files to generate the executable file. This file is generated inside the folder debug, which is inside the project folder. This file is ready to be loaded into the microcontroller chip. We will burn the program into the memory of the chip using Everdude. OK. Now, the microcontroller works in accordance with the instructions of our program. Let's check it out. Connect components in accordance with schematic diagram.